Unit 3, we're going to discuss the first and second derivative analysis and optimization problems. These are applications of derivatives, and 3.1 is on the first derivative test. So we're going to start with the definition of extrema. Or extreme value. These are your absolute maximums and your absolute minimums. So we have our y value f of c is the minimum if that value is less than or equal to all other values within an interval. Similar to that, we have f of c. Y value is the maximum if that value is greater than or equal to all other values within the interval. So this again is your absolute maximum and your absolute minimum. So that's going to bring us to the extreme value theorem. So the extreme value theorem says if f is a continuous function on a closed interval AB, and this is important, then f has both a maximum and a minimum. So it's basically a theorem that guarantees that you will have a maximum value and a minimum value so long as this interval is closed. That means it's going to contain its endpoints. Okay, so let's point out that we are guaranteed these values. So examples, what's going on here? So on this closed interval AB, I have a piece of a function, and because it's a closed interval, my endpoints are included here. And what we can see is we have an absolute maximum. The highest value, or the highest point, highest y value of all these values would be up here, the absolute max. We have a lowest point here, so that's going to be about here. And that's going to be our absolute minimum, since it is the lowest value in this interval. So a closed interval is going to guarantee that we have one of each. So let's look at what happens if it's an open interval. On an open interval, we do still have a lowest value. We can tell this is our lowest value overall. These values are obviously not lower. So we do have an absolute minimum. However, we don't have an absolute maximum, because no matter how close you pick to this point, remember that we can keep picking something a little bit higher, a little bit higher, a little bit higher each time, meaning that we don't really have a maximum value. I can keep finding a value that's closer and closer to this missing endpoint. I'm going to write that out. So again, because it's an open interval, we're simply not guaranteed to have an absolute max and min. On a closed interval, you are guaranteed to have an absolute max and min. Remember that these values, a maximum or a minimum, is a y value, a height. So that same height could occur more than once. The absolute maximum is still just that same y value each time. And we'll get into some problems that involve this later on. So let's look at a few examples. Right, finding the derivative of sine at the point 3 pi over 2, negative 1. So the derivative of sine we know is cosine. We evaluate when x is 3 pi over 2. Cosine of 3 pi over 2 is 0. So remember, what does this mean? The derivative is the slope of the tangent line. So the slope of sine at this point is 0. So that's what's happening. Let's take a look at the picture. So let's put this into a graphical perspective. If you draw out sine. So pi, 2 pi, and 3 pi over 2 negative 1 is this point here. Notice because it's a minimum, what's happening? We said there was a slope of 0. So a slope of 0 is a horizontal line. So what I want you to notice here is that this point is a minimum. There's another time in the curve when I have another slope of 0, another horizontal line, and that's going to happen up here. at this point, and this point is a maximum. If I'm just looking on the interval 0 to 2 pi, we do have an absolute max and an absolute min. But even without that, we're just looking at relative max and mins. Okay, we still have a slope of 0. So that's what's happening at maximums and minimums. It doesn't always happen, but it happens on nice, smooth functions. So that's really important to us here. We're talking about these values for a reason. So let's look at another example over here. The same thing, find the derivative of x cubed at the point 0, 0. The derivative of x cubed is 3x squared. Evaluated when x is 0, we get 0 again. So this is now the slope of x cubed when x is 0. So a little picture to see what's happening here. So when it was sine, that slope of 0 was occurring at a maximum or a minimum. Well, x cubed is a little different. So y equals x cubed looks like this. Point 0, 0 is the origin. So that's this point here. It says we have a slope of 0 at this point. So I should have a horizontal tangent line here. This point is obviously not a maximum or a minimum, but I still end up with that slope of 0. So what happens is anytime we get a slope of 0 for a function, we're finding what's called a critical number. So these are all critical numbers. Let's look at the definition of a critical number. Up with two things. A critical number is if my derivative has a value of 0, or if my function is not differentiable at a value. So let's talk about how do we know when a function is not differentiable? So these are things you'll have to pay attention to as you come across different functions. So we know sharp turns. For example, absolute value of x. Right? The linear absolute value function is going to have that V shape. So right here at the vertex, it's not going to be differentiable. Other places where a function is not differentiable. A hole in the graph. If there's a hole in the graph, we would have a critical number at that value. Same thing for any vertical asymptote. Or endpoints. Sometimes we have a function that's not a continuous function, kind of has an endpoint, such as the square root function of x. It has that starting endpoint, and it is continuous off in the other direction, but it's not differentiable here at this endpoint here. So these are all places where a function isn't differentiable, which means they're all critical numbers, as well as any time our derivative is equal to 0. So we're going to do some more examples of finding critical numbers. So let's take the function absolute value of x plus 1 minus 2. So a sketch of this function is actually a quick way to do this problem. So we know our linear absolute value function is that V shape. This is a graph that's moved 1 unit to the left and 2 units down. Still has that slope of positive and negative 1. And that's really important here because one way of finding critical numbers is to take the derivative of the function, but this isn't in a friendly form to take the derivative. So it's much faster to actually look at the slope of what you're dealing with here. The slope for this section of line is your positive 1, and the slope for this section of line is negative 1. And then, of course, at the vertex here, we have a slope. Well, we don't really have a slope. The slope is 1. The slope here is negative 1. Right here, the function is not differentiable. So critical numbers, if I'm asked to find all the critical numbers for the function, it would be where the derivative or slope of the function is 0, and we're not getting that anywhere, or anywhere where this function isn't differentiable. There's only one place where that happens, and it's when x is negative 1. So my only critical number here is when x is negative 1. So a nice square root of x function, move 3 units left. So a little half parabola there. The slope along our graph is going to change as we move along and find different points. We'll get nice different slopes, but nowhere are we going to end up with a slope of 0. It's never going to level off and start coming back down. It's going to keep increasing, so my slope will always be positive value. But right here at our kind of end point, our function is not differentiable. So again, we have another critical number, this time when x is negative 3. These are two important examples because oftentimes we're just concerned with take the derivative, set it to 0, that's how you find a critical number. Well, that's how you find it for most functions, but not for these two. So special cases, much easier to find critical numbers if you often are thinking about what the graph looks like. All right, number 5. So this is a nice polynomial function. All we have are nice whole number powers of x to the 4th minus 4x squared if we multiply. So to find, all we need to do is take the derivative and set it equal to 0. So polynomials are always nice, smooth, continuous functions for all real values. So it's not going to have anywhere where it's not differentiable. So our derivative is 4x cubed minus 8x. set that equal to 0, and all solutions here will be critical numbers. So a little factoring. So I have when x is 0, that's one critical number, and I have when x squared equals 2, or when x is plus or minus square root 2. So my three critical numbers, 0, plus and minus root 2. Before we go on to the last example, we're going to talk about the first derivative test. Right. So we're going to have a continuous function on a closed interval. So that means the endpoints of the function exist. Differentiable on the open interval AB. This is because we can't be differentiable at endpoints, which was our example back up here for number 4. So differentiability is always on an open interval, but we need continuity on the closed interval at the endpoint. We have 3 cases. So we have, if our derivative is positive for all values in an interval, then our function is increasing on the interval. So similar to that, if our derivative is negative for all values of x on an interval, then the function is decreasing on that interval. Well, there's obviously a third case because functions don't always increase or decrease. There's one more thing that could happen. If my derivative is equal to 0 for all values in an interval, then the function is constant. For example, a horizontal line is going to be a constant function, so the slope of that line for all values is 0. So that's going to be that case. And that can happen for pieces of graphs, so you'll watch out for piecewise functions as well. So that's the first derivative test. So how do we do the first derivative test? So let's go back up here to number 6. And we're going to use problem number 5 and test it. So it is a polynomial. I know there's not going to be anywhere where the function is constant, so I'm looking for the intervals where the function increases or decreases. So there's some things we know. Its highest power is 4, so end behavior of the curve is high to high. It should decrease, it should increase. It may do that a few times. We're going to use our values to test here. So to find intervals where my derivative is positive, negative, or equal to 0, you actually do start by finding your critical numbers. So step 1 Find all critical numbers of whatever function you're working with, and that does include anywhere where it's not differentiable. For our function here, all we have are 0, plus, and minus root 2. Second thing we're going to do is place these values on a number line. So not just any number line, this is the number line for my derivative. So because it's called the first derivative test, this is my test for the first derivative. So always label your number lines. Eventually we'll get into second derivative tests where you'll need to label the line f double prime. For now, you need to label it f prime so that we know which test this is. We have negative root 2, 0, and root 2. On top, what's the value of the derivative at negative 2? Negative root 2, 0. The value of the derivative at 0 is 0, and at root 2 it's also 0. So I'm just putting the value of my derivative here. If any of these critical numbers were places where my derivative did not exist, or where the function is not differentiable, I'd write D and E on top. So we're just going to write 0 for now. And then in between the intervals, we're trying to figure out if it's positive or negative. So I know I'm not going to get 0 for any of these intervals. So we need test numbers. So something smaller than negative root 2, negative 2 would be a good test number. Something in between, we'll use negative 1, 1, and 2. Where do these numbers get plugged into? That's why we label it, again, f prime. That tells us exactly where to plug all of these into. So if I plug negative 2 into our derivative, we're going to get a negative times a positive, which is negative. If we plug in negative 1 to our derivative, we'll get a negative times a negative, which is positive. If we plug in 1, we get 4 times negative 1 is a negative. And when we plug in 2, we get 8 times 2 is a positive. So now we just go back to our test down here and fill these in. It says anytime our derivative is positive for all values in an interval, that would be these two intervals here, our function is increasing. So beneath, I'll write out what's happening for f. F is increasing on the interval negative root 2 to 0 and the interval root 2 to infinity. And second, anytime my derivative is negative on an interval, my function is decreasing. So f is decreasing from negative infinity to negative root 2 and from 0 to root 2. So now it's just a matter of writing that out. F increases, I might just abbreviate that, on the interval negative root 2, 0, root 2 to infinity. And then f is decreasing from negative infinity to negative root 2 and 0 to root 2. And that's how we apply our first derivative test. Find your critical numbers. That includes all zeros of the function, of the derivative, and all places where the function is not differentiable. And then we place them on a number line for the first derivative and test that first derivative. We interpret negative intervals where the function decreases, positive intervals where the function is increasing. If you happen to get an interval where all the values keep spitting out zeros, that's when our function is constant on an interval.